In the system design, we know that application connected to the web application is using somehow either TCP protocol or QUIC protocol. And I have also showed you that you can create a code by which you can actually allow your application to use either TCP or QUIC. In the last part, we discussed about the TLS handshake in the TCP, but to understand the complete picture, what is suitable for your application and how these transactions work, because anyhow, the system design is for something to increase the speed of your application, increase the workability of your application. So this understanding of QUIC TLS handshake is also required. In the last part, we have discussed the above two questions, which you are seeing on the screen right now. So I want you to just pause the screen right now, go through all these five questions. If you are able to answer these all five, then definitely this lecture is not for you. But still, if you are having any doubt, like why and what, then I will recommend you to watch this part. So pause the screen and read all the questions. Okay, I guess you have figured out that either you need this video or not. So based on, if I'm assuming that you need this video, then I can start with the part of QUIC TLS handshake, and then we can answer these all five questions one by one. Okay, so let's come here and we will start with the part QUIC. Okay, where it is? Here it is. QUIC TLS handshake. Don't worry, I will tell you about all the version. In QUIC, TLS is used as 1.3. It is the 1.3 version. And QUIC is a quick UDP internet connection. And this QUIC is used by the Google. And lots of application where you are seeing the incredible fast speed happening when you are querying something, when you are accessing something. So to understand how this QUIC TLS handshake work, we need to first understand that, let's say it is the client. What is the client? Client is the one who wants something from the web application, and it is the web application. This web application is running on web server. Okay, so it is running on web server. It is the client. Client can be your PC, your phone, your laptop. It can be anything which is querying a website. So when this client is making connection to the web application through the QUIC, then it sends some QUIC packet. Okay, this packet is something which contains the detail of what type of connection it is and what are the other details. Okay, I will show you everything. So let me just move it a bit. Fine. So let's start with the QUIC packet. Okay, so here is the QUIC packet, the data packet. There's a one thing which we need to know, that this QUIC is very efficient. It In the earlier parts, we did the handshake between the client and the QUIC, the client and the web application, and to use the QUIC. But this TLS handshake is also happens simultaneously in the same cycle. And how it happened? Because it contains three parts. What is this? First is header. There is no need to go inside the other tool to see what's the packet structure. All you need to understand is what are the parts are there, because it is the only thing which we need to understand to provide the answers in the interview. So it have this QUIC packet have one header, it have this frame, and then it have this TLS message. Okay, so it have these three parts. So currently in header, it have the version detail, it have the data of packet type. Okay, let me just erase it. Okay, fine. What is the type of packet? Packet type. And then it contains the detail of data connection ID, data connection ID. So in the earlier parts of this system design series, I told you that this QUIC, when it create connection with the web application to client, then it provides some connection ID, the source connection ID and the destination connection ID, and it is that connection ID. Okay, so this is the header, and coming to the frame, it contains the offset. We have discussed a lot about this offset in the earlier part, but still, for those 5 questions, this concept is not required. Okay, and what else it needs? It contain the frame type. Okay, there is no need to understand this as well for now. But when we go for the advanced one, when we are going to actually apply this particular packet for our web application, then we will see the complete structure of this offset frame. But for now, just remember, like, these are the parts of this particular QUIC packet. And what we need to focus is we need to focus on the TLS message. So this TLS message will contain the key share, and it contains the cipher suit, which cipher it will use. Then it contains the handshake type, and also it contains the transport parameters. This is one something key share. It is the very important part which we are going to discuss in this particular video. This key share is something which make this TLS handshake happen in the QUIC. So let's go further with bit more detail. So till now, what we have understood that, okay, for the client to be connected with the web application using the QUIC protocol, it need a QUIC packet. This QUIC packet contains the header, the frame, the TLS message, and this TLS message contain the key share, cipher suit, handshake type, and transport parameter. This handshake type is, let's say, it can be client hello. Okay, let me just write it down here. It might be client hello, or it might be server hello. So whoever is sending that comes into the handshake type. Okay, so let me just go in bit more details that what is this key share. Okay, so coming to the part of TLS. Okay, let me just write it. Okay, so here is the TLS in QUIC. So for the TLS in QUIC, there is very good mechanism which we can say is used here to create a reliable connection between the web application and your client. And how it do? Okay, so let me just draw one client here. Client can be anything, and it is your web server. So how these things process? So what it do is it uses the, okay, let me just change the pen. It uses the ECDH. ECDH. It is called as elliptical, elliptic, curve, elliptic curve, elliptic curve Diffie, elliptic curve Diffie. Okay, let me just remove this one for now. Okay, what's happening? What happened? Okay, elliptic curve Diffie-Hellman, elliptic curve Diffie-Hellman. Might be some spelling wrong, I'm assume, but it used this ECDH method. What is this ECDH method? And this QUIC used this ECDH method to create a connection between the client and your web application. But what is this ECDH? ECDH, okay, let's see this in action, then only we can understand that why this ECDH is required to create the QUIC and why it is fast. Okay, so what I will do, I will just come here and we'll change the pen. Okay, so here again we have this client and we have the web server. What they both will do, they will create a temporary private key and public key. They both will generate private key and public key. It is for the client and it is for the web server. Private key and public key. For now, let's assume this private key is small a and this public key is capital A. For the same, this for the web server, this private key is small b and this public key is capital B. And there is this one constant. This is called G. This constant is called as mm, predefined base number. Okay, so it is a base number. So if you go to this ECDH, there is the document you will get, and in that document, the number G, this base number, is defined with value, and it is publicly used as it is. There is no change in that G. You can find it in a document, and there is no secrecy in it. But how this thing work with each other, that we are going to understand. So what I will do, I will just do a little more drag here. Okay, so here, okay, fine. So for the there here is the client and here is the web application, web server. So here this A is the private key and this capital A is the public key. Here small b is the private key and capital B is the public key. And there is this base number G. So it is calculated in a way that this small a into G equals to capital A. It means if you multiply this base number to the private key, then you will get the public key. Same goes with the web server. So if you do the private key multiplied by this base number, it will generate the public key for the web server as well. And as I told you, these are the temporary secrets. These are not uh, the secrets which will stay forever inside the system. They will delete it. So that is why it is secure too. Okay, so right now, what the client will do, client want to create a connection with the web server. And what this client will do, client will send this public key. Client will send this public key to the web server because we do not share the private key. We share only the public key. It means what it is sending this A cross G. So currently with this web server, here we have this A cross G, and also we have this uh, B cross G, and same the web server will send its public key to the client. So currently the client have this A cross G and B cross G. Okay, so we at both sides we have this A cross G and B cross G. This is the public key. It is the public key, and the small a is the private key. So we have shared the private key. Sorry, we have shared the public key, not the private key, but still we have these kind of formulas at both the side. But right now, what will happen is they need to create a something like this. They need to create a equation something like this. Then how it will create? So to create it, as I told you, this small b is the private key. It is already present at the web application side, web server side, and this A cross G is coming from the client, which is known as A. So we have this A into B. It means A cross B cross G we already have at the web server. The same calculation will happen at the client side too. So at the client side, we have this B cross G, and also we have the private key as well at the client side. So again, it will be similar to A cross B cross G. Now, at both sides, we have something similar because these all are some mathematical equation. These all are some encrypted data. So it will provide one common secret. So with this calculation, like this capital B comes here and the small a, like it formed A into B into G. Again, the same, this A into G comes here and the small b was also present at the web server side. So again, it also created A into B into G. So it is this ECDH calculation. It is the ECDH algorithm. By this, we at the client side, at the web server side, they both have the common secret. They have the secret. Now they can start communicating with each other. Okay, let me just drag it a bit more. Okay. So right now, okay. So right now there is this common secret. Common secret. Let's call it X. Let's call it X. So here is my client, and here is my web server. So here the web servers also contain X. Sorry, the client also contains X. This web server also contains X. And every time when this particular client will try to send data to the web server, they both will verify that this X is identical or not. If it is identical, then you are welcome. And if this is not identical, I'm sorry, you cannot process it. And because these are the temp secrets, these are only created at the client side, these are the only created at the web server side, then there is no way any hacker can generate their secret and they can match it with yours, because it is completely related to the client machine and this is completely related to the web server machine. Amazing. It is really amazing. This ECDH algorithm is totally mind blowing, that how they simplified the calculation of the secrets so that you and your web application can communicate with each other in a safest way possible. And these all things happen in a single cycle when you are doing the QUIC. So in the QUIC, first it will do the handshake of connection, handshake, connection handshake, and TLS handshake. They both will happen simultaneously in a single cycle. So in this way, the TLS handshake work in the QUIC. Now let's time to understand that how this QUIC and TLS 1.2 with TCP and TLS 1.3 with TCP provide the uh, RTTs, round trip time. Okay, so for that, what I will do, I will just drag it here and I will create something like, okay. So in the QUIC, it will take only one RTT, round trip time, round trip time, because in a single RTT, it will do the connection and TLS. So let's assume it is taking 200 milliseconds for this one RTT. So in a 200 milliseconds only, you and the Google is connected to each other and ready to start the communication. Let's come to the TCP with TLS 1.3. TLS 1.3. In QUIC, it is also used with TLS 1.3. Okay, so this TCP and this TLS is using with TCP used with TLS 1.3. How many RTT it will take? It will take 2 RTT. Why 2 RTT? 1 RTT for its acknowledgement sync cycle, and second RTT for the private and public key calculation, which we did in the earlier part. So for the secret and this encryption. Sorry, yeah, encryption, the secret and encryption transfer. So in the best case, the QUIC will provide you 1 RTT with the 200 milliseconds. It will provide you the 2 RTT. It means if 200 milliseconds is the time of one round trip, then it will take 400 milliseconds. Now comes the part of TCP TLS. Okay, okay, right. Okay. So if I am going to use the TCP with TLS older version, it is not widely used right now, but still, if you want to learn, it will take 3 RTT. And how it will take 3 RTT? The 1 RTT standard for the acknowledgement and sync process. Second RTT, 1 RTT is for TLS handshake, and another RTT for key exchange. It is the key exchange. key exchange, they will exchange the public and private key. Sorry, they will exchange the keys to each other. I don't know much about the TLS 1.2, but the explanation which we did earlier was for the TLS 1.3, and we need to focus on the latest trends only. So here it will take around 3 RTT. It means it will take around 600 milliseconds. Okay, so right now we got the calculation that how these all things work. So we can create a very simple table here. Okay, so for the QUIC, it is the fastest 1 RTT and it will take around 200 milliseconds. These are just example time. Then coming with the TCP with TLS 1.3, it will take 2 RTT. It will take around 400 milliseconds. And TCP with TLS 1.2, it will take 3 RTT, which will take around 600 milliseconds. So as per the speed, this QUIC won the match. But still, as I told you earlier, this TCP with TLS 1.3 is still used in so many applications because of its reliability. It is so much reliable that it will not even lose a single bit while transferring the data. It will make sure that yes, your data is transferring bit by bit and completely to your client side or to your server side without any loss. So this TCP with TLS 1.3 is still used, and it is used where the speed doesn't matter. See, we are in the world where everything is needed as quickly as possible, but still we need the reliability as well. So reliability have more weightage than the speed. So that is why this TCP with TLS 1.3 is still in use till now. There is a one more concept of zero RTT. What is this zero RTT? Is it possible to have this no delay with the connection? Yes, it is possible. It is possible when, let's say, you have this client and you have this web server. You have already created one connection earlier. Let's say yesterday you have created the connection and you did the cycle of this 1 RTT, 2 RTT, and 3 RTT. Again, today you came and you you want that I want to connect with the same application. Or after a few hours, you came back, you logged into the server and you said like, I want to do the work again. So in that case, what QUIC will do, QUIC will have this source ID, this destination ID. It is already saved at your system, at your cache, and using the source ID and destination ID, it will immediately start transferring the data, or it will immediately start uh, working on your request response. So in this way, this zero RTT applicable on the client and web server when we are using the QUIC. In the case of TCP with TLS 1.3, this zero RTT is also there. Same. If the connection already established once, then there is no need to create the again acknowledgement and synchronization cycle. All we need to do is we need to use the available channel. But the only thing is this with the TCP and TLS 1.3, that particular pipeline is still available at the time when you are going to reestablish the connection. It means when it comes to TCP with TLS 1.3, there is some timeout, and if that timeout happened, then again you need to do the complete cycle. But with the QUIC, there is source ID and destination ID. Again, there is a timeout thing, but its timeout is a bit more. You can set this timeout. There is no definite cycle for it. You can set this timeout in your application, in your code, and based on that, you can perform these operations. So this zero RTT is something when the source ID and the destination ID is still available at the system and the web application side, and the user just want to start the communication. Then by using these two things, the backend system automatically start transferring your data without doing any handshake or without requesting any synchronous or acknowledgements request. So this is the complete thing with the QUIC, TCP, and TLS 1.2. Sorry, with the TCP and TLS 1.2, this 0 RTT is not available. Only with the 1.3, it is available. So let's come back to the part where we were handling the questions of system design. Okay, so let's start again from question 1 to question 5, and let's see if you are able to answer these questions or not now. So I want you to stop the screen and just go through all the questions. After that, I will just go through all the questions one by one, and we will get a very simple answer for it. Okay, so again, let's go for the why does TLS use both asymmetric and say symmetric encryption? Why not just asymmetric encryption for the whole session? So this asymmetric encryption is costly, it is time consuming. That is why it happened only one time, and in that one time only it do the complete process which is required for the connection establishment. Like it will do the exchange of encryption keys and the method and the encryption keys, the which encryption is this connection is going to use. That is why it is just happens only one, and after that this symmetric encryption happen, and this symmetric encryption will continue till the end of the session. A man in the middle attack intercept the connection, blocks the server public key, and send their own public key to the client. How does the browser know it's being tricked? Again, it is related to the uh, CA certificates. This what is called this SSL certificates. So we can still stop this question for now, and we in the next part when I'm going to tell you about this SSL certificates, this CA certified SSL certificates, then we will understand that okay, what this particular question means. Walk me through the round trip time latency of establishing a secure connection using traditional TCP TLS 1.2 versus modern QUIC. So it is the older version of TLS with their TCP. So it is taking 3 RTT and the QUIC is taking 1 RTT. So you have the answer. You mentioned QUIC can achieve 0 RTT. How is it physically possible to send secure data with zero setup time? Is there a security trade-off? No, there is a no security trade-off. All you need is like you already have one established connection between the web application and the client. Once this connection is already established and it is not timed out, then you can use the 0 RTT. Sorry, not you can use the 0 RTT. Actually, it will not do the operation of this synchronization and the sharing secret. It just start using that source ID and destination ID and start the transfer of request response and data. So that is how this 0 RTT happened. Imagine a hacker record months of encrypted traffic between a client and a server. Years later, they managed to steal the server's private key. Can they decrypt all that past traffic? So I will say no, because this Q5 is for the QUIC, first of all, and that particular private key which we have created while running the QUIC, those were the temporary secrets. Those temporary secrets creation is bit different than uh, the private keys which we actually generate to access the system. So even the hacker have the thousands of records like for so many years from past so many years, but still they will not be able to hack into my system. The detailed version of this answer is present into the description, but still I want you to understand these questions in a way so that you can answer. There is no need to learn in a bookish language, but still for reference, the detailed bookish answer is present into the description. So that's it for this part. And in the next part, we are going to understand this how CA certificates, these SSL certificates, help me to identify that something is coming from a hacker or something is coming from the valid application. Thanks for watching this video. And if you have any question or if you have any doubt, then please let me know into the comment section. I will definitely try to answer it. And thanks for watching.